In this video, I will explain primary and secondary constants of the transmission line. Primary and secondary and secondary constants. Constants of the transmission line. Consider a two-way transmission line shown in figure. Here, two-way transmission line is shown in figure. Here, Vs, Is are voltage and current at a source. That means sending end. This one is Vs, voltage. This one is Is, current. Here Vs, Is are voltage and current at source are sending end. This one is a sending end. And the H is the magnetic field intensity. This one is a magnetic field intensity is like that. Magnetic field intensity. And E is the electric field intensity. E is the electric field intensity like that. E is the electric field intensity. ZL is load impedance. ZL is load impedance. VR is voltage at the load. VR is the voltage at the load at the receiving end, at the receiver end. Z is equal to 0. Z is equal to L, where L is the length of the transmission line. This one is the description of the transmission line, two-wire transmission line. When a current is passing through the line due to applied voltage across the two conducting wires, then there exists a voltage drop within the conductor. This is the Is. Is is the current passing through the line due to applied voltage Vs across two conducting wires. This is conducting wire 1, conducting wire 2. Then there exists a voltage drop within the conductor. These two are the conductor lines, conductors. This indicates that the line is having some series resistance. The line is having some series resistance R. And also there exists a magnetic field around the conductor H shown in figure due to flow of current through the conductor, which indicates that the line is having a series inductance. This indicates that the line is having some series inductance L. Okay. Due to applied voltage across two conducting wires, Vs is the voltage applied across the two conducting wires. The charges are built on them. The charges plus the minus are the charges built on them, which indicates that the line is having some capacitance, that is some shunt capacitance, that is C. The capacitance can never be an ideal one. Some losses are there. The capacitance can never be an ideal one. It has some leakage conductance G. It has some leakage conductance G. Like that. The four parameters, resistance, inductance, capacitance, and conductance are the primary constants which are distributed throughout the transmission line. The four conductors, the four parameters, not conductors, the four parameters, the four parameters are resistance, inductance, capacitance, and conductance are, are the primary constants, are the primary constants, which are distributed throughout the transmission line shown in figure, which are distributed throughout the throughout the throughout the transmission line shown in figure above. If they are distributed uniformly, then the line is said to be a uniform transmission line. Just like the two-way transmission line, just like the two-way transmission line. The resistance, inductance, and the capacitance and the conductance are the primary constants of the transmission line. Here R is the defined as loop resistance. R is the resistance per unit length. R is the resistance per unit length. Unit is mho per meter, ohm per meter, not mho. Next one, L, inductance. L is the inductance per unit length. Inductance per unit length. That means Henry per meter. Henry per meter. C, capacitance. Capacitance per unit length is the capacitance per unit length, farad per meter. G is the conductance per unit length. G is the conductance per unit length. Siemens per meter. Siemens. These are the primary constants. Next one, secondary constants. Secondary constants of the transmission line are characteristic impedance of the transmission line and propagation constant. Secondary constants. Secondary constants, which are characteristic impedance, impedance, characteristic impedance Z0. Second one is propagation constant gamma. Propagation constant gamma. These are the secondary constants of the transmission line. Next, characteristic impedance. Characteristic impedance. The characteristic impedance of the transmission line is defined. Consider two equations here. Consider two equations. That is Vs of Z is equal to V0 plus e power minus gamma Z plus V0 minus e power gamma Z. Is of Z is equal to I0 plus e power minus gamma z plus I0 minus e power gamma z. Consider these two equations, transmission line equations in phasor form. Derivation of that characteristic impedance. We know that d by dz of Vs of z is equal to minus r plus j omega l Is of z. Is of z. D by dz of Vs of z is V0 plus e power minus gamma z plus V0 minus e power gamma z. V0 plus and V0 minus as the amplitudes of the wave in positive z direction and negative z direction is equal to minus r plus j omega l Is of z is equal to I0 plus e power minus gamma z plus I0 minus e power minus gamma z plus gamma z. Differentiate this equation. V0 plus e power minus gamma z d by dz of e power minus gamma z is e power minus gamma z minus gamma plus V0 minus derivative of d by dz of e power gamma z is e power gamma z into gamma is equal to minus r plus j omega l into I0 plus e power minus gamma z plus I0 minus e power gamma z. The wave is propagation along z direction. The equating the coefficients of the coefficients of the coefficients of e power minus gamma z and e power gamma z on both sides on the both sides of the equation. Both sides of the equation. Above equation. E power gamma minus gamma z coefficient is minus gamma V0 plus here minus r plus j omega l I0 plus. The quotient of e power minus gamma z, quotient of e power minus gamma z, quotient of e power minus gamma z, e power minus gamma z is equal to minus gamma V0 plus is equal to minus r plus j omega l I0 plus. Quotient of e power gamma z is equal to gamma into V0 minus is equal to minus r plus j omega l I0 minus where gamma is the propagation constant is square root of r plus j omega l and g plus j omega c propagation constant. From this equation minus is cancelled. V0 plus by I0 plus is equal to r plus j omega l by gamma. This r plus j omega l is written as square root of r plus j omega l into square root of r plus j omega l. The meaning is same. Here gamma is square root of r plus j omega L into g plus j omega c is written as r plus j omega L square root of r plus j omega L into square root of g plus j omega c. These two are cancelled. Is equal to r plus j omega L by gamma. R plus j omega L written as square root of r plus j omega L into square root of r plus j omega L by gamma is square root of r plus j omega L into square root of g plus j omega c. These two are cancelled. Therefore, V0 plus V0 plus by I0 plus is equal to square root of r plus j omega L by g plus j omega c. And consider coefficients of e power gamma z is equal to gamma v naught minus is equal to minus r plus j omega L I naught minus. Therefore, v naught minus by I naught minus is equal to minus r plus j omega L by gamma. That is equal to minus r plus square root of r plus j omega L into square root of r plus j omega L. Gamma is equal to square root of r plus j omega L into square root of g plus j omega c. These two are cancelled. V0 minus by 0 minus is equal to minus of square root of r plus j omega L by g plus j omega c. It is called as characteristic impedance of the transmission line. It is denoted by Z0. Therefore, Z0 is equal to square root of r plus j omega L by g plus j omega c. Three definitions of characteristic impedance. First one is the ratio of forward voltage. The ratio of forward voltage wave to the forward current wave at any point on the line. Z is equal to Z0 is equal to V naught plus by I naught plus. The characteristic impedance is also defined as ratio of forward voltage wave. That means V0 plus to the forward current wave, that is I0 plus at any point on the line. The characteristic impedance is also defined as the negative of V0 minus by I0 minus negative of the ratio of a reverse voltage wave to a reverse current wave at any point on the transmission line. Minus VR minus by IR minus negative of negative. This is the characteristic impedance. This is the secondary constant. Next one, propagation constant, gamma. Gamma is propagation constant. Propagation constant gamma. Gamma is equal to square root of r plus j omega L into g plus j omega c. This one is a transmission line having some inductance and resistance and capacitance and conductance like that. R, L and R, C, G. That is Z is equal to R plus J omega L. Here Y is equal to J omega C plus G. Therefore, gamma is equal to square root of series impedance to shunt impedance. Series impedance, series impedance, series impedance to into shunt admittance. Shunt admittance. Series impedance means Z R plus J omega L. Shunt admittance means G plus J omega C. Gamma is equal to square root of Z into gamma is equal to natural logarithm of the ratio of the sending end current or voltage to the receiving end current or voltage of the line. Vs by VL or Ln Is by IL. This is another definition. Gamma is equal to propagation constant. Gamma is equal to alpha plus J beta, where alpha is attenuation constant. Alpha is attenuation constant. Attenuation constant. dB per meter. Beta is a base phase constant. Beta is phase constant. Radians per meter. Radians per meter. Gamma is equal to gamma is equal to alpha plus J beta. Alpha plus J beta is equal to gamma is equal to square root of R plus J omega L into G plus J omega C. Squaring on both sides is equal to alpha plus J beta whole square is equal to R plus J omega L into G plus J omega C. That is equal to RG J omega LG plus RC J omega LG plus RC, that is RC minus omega square LC. Equating real parts and imaginary parts, that is alpha square plus beta A square plus B square plus 2J alpha beta. Equating real part of the equation, that is alpha square minus, this one is minus. This one is minus alpha square minus beta square is equal to RG. This one is real term, RG minus omega square LC. Gamma is equal to alpha plus J beta. Mod gamma is equal to square root of alpha square plus beta square. Alpha square plus beta square. We know that gamma is equal to, equating this one, mod gamma. Gamma is equal to square root of R square omega square L square plus G square omega square C square, mod gamma. These two are equal. Mod gamma alpha square plus beta square. This one cancel. Therefore, alpha square plus beta square is equal to square root of alpha R square omega square L square G square plus omega square C square. But alpha square minus beta square is equal to alpha square minus beta square is equal to RG minus omega square LC. Add these two equations. We will get one expression. 2 alpha square is equal to 2 alpha square is equal to Rg minus omega square LC plus square root of R square plus omega square L square G square plus omega square C square. That is alpha is equal to 1 by 2 Rg minus omega square LC plus square root of R square plus omega square L square G square plus omega square C square. Total root. This one is total root. From equations alpha square plus beta square, alpha square minus beta square. First we will add, we will get alpha and subtract these two equations. Therefore, 2 beta square is equal to Rg minus omega square LC minus square root of R square plus omega square L square G square plus omega square C square. Therefore, beta is equal to square root of 1 by 2 omega square LC minus Rg plus square root of R square plus omega square L square into G square plus omega square C square. With this, the two are completed. Alpha is the attenuation constant. Beta is the propagation constant. Beta is the phase constant. Gamma is propagation constant. Primary constants of the transmission line are resistance, inductance, capacitance, and conductance. The secondary constants of the transmission line are characteristic impedance and propagation constant gamma. Propagation constant is gamma. With this, the analysis is completed.